Ever wonder how Netflix just knows what you want to watch next? Or how Google can search, well, the entire internet in a blink? The answer to all of that comes down to big data. So today, we're going to build a modern big data system right from the ground up. We'll look at the core ideas and the tools that really change the game. Let's jump in.
You know, this question really gets to the heart of the whole big data problem. The amount of information we create today is just staggering. It's like that infinite library. Your regular computer, a traditional database, they just can't handle it. They were never ever built for this kind of scale. So here's the plan. First, we'll nail down what the problem actually is. Then we'll tackle the first big challenge. Where do you even put all this data? After that, we'll look at the engines that do the heavy lifting, the processing. And to wrap it all up, we'll see how the cloud makes all this powerful tech available to pretty much everyone.
Right, so the main takeaway here is that we needed a totally new way of thinking. See, the old systems, they were great for neat, tidy data that could live on a single computer. But big data, it's messy, it's enormous, and it's coming at you at lightning speed. This called for a brand new architecture, one built on a simple idea: spread the work out across lots and lots of machines. And that leads us to the first giant hurdle: storage. I mean, if you can't save the data, you can't do anything with it, right? The solution was something called a distributed file system. It's a clever way to make a whole room of computers act like one single, gigantic hard drive.
So who had this problem first and at the craziest scale? Yep, Google. To power their search engine, they had to invent their own solution. They called it the Google File System, or GFS. It was built from day one to do two things really, really well: handle huge files with incredible speed and be fault-tolerant. That just means if one computer in the network goes down, the whole system doesn't care. It just keeps on chugging along. And the way it works is actually pretty brilliant. You've got one master server that's kind of like the librarian. It doesn't hold any of the books, but has a card catalog that knows where every single piece of information is. Then you have tons of chunk servers, and they store the actual data, which is broken up into these big chunks. So when you need a file, you ask the master, hey, where are the pieces for this file? The master tells you, and then you go talk directly to the chunk servers to get what you need. It's this smart division of labor that makes it so incredibly fast and efficient.
Now, this is a key moment in the story. GFS was a total game changer, but it was Google's secret sauce. No one else could use it. The rest of the world saw what was possible and thought, we need that. This demand for a version that anyone could use, anyone could build on, that was the spark for the next huge leap forward.
And that brings us to HDFS, the Hadoop Distributed File System. It's basically the open-source answer to GFS, inspired directly by the paper Google published. It runs on the exact same core ideas. You have a central name node, which is the librarian, and a bunch of data nodes that store the actual blocks of data all across the computer cluster.
This comparison really lays it all out. You can totally see that HDFS is the spiritual successor to GFS. But look at that first line: ownership, proprietary versus open source. That one single difference is why HDFS and its whole ecosystem, Hadoop, absolutely exploded. It became the de facto standard for big data storage for years.
Of course, just storing huge files isn't the whole story. What about more structured stuff, like all the data in a search index? For that, Google built Bigtable. It's what we call a NoSQL database, which really just means it's not like your classic spreadsheet-style database. Instead of rigid rows and columns, it's more like a gigantic, perfectly sorted map. This lets it grow to almost any size and still grab data super fast. All right, let's keep building. So we've got our foundation for storing petabytes of data using HDFS. Awesome. But now, how do we actually do anything with it? How do we find that single word in our infinite library? We need a processing engine.
The first big processing framework, again, pioneered by Google and adopted by Hadoop, was MapReduce. It's this really elegant model that makes it simple to run jobs across thousands of computers at once. It breaks down any massive task into just two simple steps: a map step and a reduce step.
The classic word count example shows this perfectly. So in the map phase, a function just goes to the text and spits out a key value pair for every word. It sees big and makes big 1. It sees data, makes data 1. Simple. Then comes the magic. The system automatically shuffles and sorts all those pairs, so all the identical words get grouped together. Finally, the reduce phase takes each group and just adds up the ones. And boom, you have your final count for every word. It seems simple, but when you do this across thousands of machines at once, you can analyze an unbelievable amount of text.
But MapReduce had a bit of an Achilles heel.
In between every single step of a job, it would write all the results back to the slow hard drives in HDFS. Now, for a simple, one-off job, that's okay. But for anything more complex like machine learning algorithms that have to run over and over, all that reading and writing from the disk became a serious bottleneck.
And the answer to that problem was a new idea called the Resilient Distributed Dataset, or RDD. This is the absolute core concept behind Apache Spark, which is pretty much the successor to MapReduce. The big idea was revolutionary. Instead of constantly writing to slow hard drives, let's do as much of the work as we can in the computer's super-fast memory, or RAM.
Now, RDDs have a few really important properties, but the absolute game changer is right there at the bottom, in-memory computation. By keeping all that intermediate data in RAM, Spark could run jobs up to 100 times faster than MapReduce. This just blew the doors open for things like interactive data science and real-time analytics.
So here's the evolution in a nutshell. Think of MapReduce as the super reliable heavy-duty truck. It's great for those huge one-time jobs. But Spark, with its in-memory RDDs, that's the high-performance race car. It's built for speed, for iterative tasks, and for interactive analysis. Two powerful tools, just built for different kinds of races.
Okay, time for the final piece of our puzzle. We have a storage system, we have a processing engine, but where do you actually run all of this stuff? Building out your own data center with thousands of servers is, crazy expensive and ridiculously complex for most people.
And this is exactly where the cloud comes in. It is the perfect environment for this. You get what's called elastic scalability. You can fire up 1,000 machines for a huge job and then turn them off an hour later. You get cost efficiency because you only pay for what you use, and of course, it's all accessible from anywhere in the world.
And this is really where the story comes together for everyone else. The big cloud providers like Amazon, Google, and Microsoft took these amazing open-source tools and turned them into easy-to-use managed services. This was huge. It meant that suddenly, with just a few clicks, anyone, a startup, a researcher, you, could launch a massive big data cluster that would have cost millions of dollars to build just a decade earlier.
So there you have it. We've stacked all the blocks together. At the bottom, you have a distributed file system like HDFS to store the data. On top of that, a super fast in-memory engine like Spark with its RDDs to process it. And it's all running on scalable pay-as-you-go infrastructure in the cloud. That right there is the modern big data stack.
The journey from GFS being a secret tool inside Google to these powerful platforms being available to everyone on the cloud, it happened incredibly fast. This evolution never stops because our appetite for data just keeps growing. So that leaves us with one final fascinating question to think about. What's the next big problem we're creating today that's going to need a whole new building block tomorrow?